Hey everybody, I'm going to work a practice problem from the textbook on LeChatelier's principle. So this should help you guys kind of understand what I walk through on the video with LeChatelier's principle, but then see it worked out on a problem. Very much like, any problem you could see on a quiz or an exam. So hopefully this is helpful. I picked an odd number problem, so the answer is not in the back of the textbook. So that's helpful because you can easily check yourself on even numbered problems. But here in this problem it says oxygen can be converted into ozone by the action of lightning or electric sparks. Okay, so we have O2, 3, coefficient of 3, O2, it's gas, converted to ozone, which is O3, and that's a gas as well. It says for the reaction, delta H is a positive 68 kcal per mole, or it gives us the value in kilojoules per mole as well. And then it says K is 2.68 times 10 to the minus 29 at 25 degrees Celsius. And then it just asks a series of questions. So I'm going to zoom in on some of these questions. The first question is, A here, is the reaction exothermic or endothermic? So if delta H is positive, okay, I see a positive 68, that lets me know that immediately that it's endothermic, okay, endothermic. I could ask you, is heat then a reactant or a product, okay, and heat would be here a reactant. You would say heat, or you could say heat plus oxygen, or you could write 68 kcal per mole plus oxygen, and that would give you your ozone. Okay, so heat. This is definitely endothermic reaction, right? B, are the reactants or the products favored at equilibrium? Okay, so K. To determine this, we're going to look at the value of K, and I have K underlined over here. K is times 10 to the, look at this minus sign right here, okay, 10 to the negative 29. Is that a really, really big number or a really, really small number? Well, anything to the power of negative is a decimal, okay, really small, and I'm not going to actually write out the standard number for that, but it's an incredibly small number. Here's what we know. K is much, much, much smaller than 1, okay, so if you remember that whole arrow, I had the arrow right here. Okay, remember when K is much, much, much smaller than 1, we're in the red section, okay? We're somewhere down here. K is way smaller than 10 to the minus 3. Reaction hardly goes at all. We said forward reaction does not occur. Reactants are favored completely, all reactants. So here we're going to say reactants are favored, okay? No products. We're not going to get any products. All right, C. Here's the LeChatelier's principle part. Explain the effect of equilibrium on all these different scenarios. Let's just look at the first one. Increasing pressure by decreasing volume. So I'm going to focus on this increasing pressure because, same thing if we're decreasing volume, we're increasing pressure. But I talk through scenarios of pressure on the LeChatelier's principle video. So how do we determine if equilibrium is going to shift right or left? So remember, to do this, you assess how many moles of gas do you have on each side. Here we have 3 moles of gas, okay, 3, and they're all gases. That's the only thing we have. And then on the other side, we have 2 moles of gas, okay? So if we're increasing the pressure, we said that equilibrium is going to shift to the side with fewer moles of gas, okay? Equilibrium will shift to the side with fewer moles of gas if we increase pressure. And that, for this equation, it won't always be the same side, but for this equation, that is the right side. So here, equilibrium, I guess I should write EQ, will shift to the right. Okay, if the fewer number of moles of gas is on the right side, here it's going to shift to the right. But it will always shift to the side with fewer moles of gas if we increase pressure. Okay, number 2, increasing the concentration of O2. Let me erase all this. If we're increasing the concentration of O2, I'm going to put an upward arrow here. That's like we're increasing this. So LeChatelier's principle says if we increase the concentration of a reactant, that equilibrium will shift to minimize the effect of that change. So we're going to use sum up by breaking it down, or by converting it into ozone. Okay, so if we increase the concentration of our reactant, it's going to shift towards the product. So again, equilibrium will shift right here. Number 3, increasing the concentration of O3, which is ozone. This is our product this time. Okay, so let me erase. And if we're increasing the concentration on this side, okay, if we're increasing the concentration, then equilibrium is going to shift to minimize the effect of that change, okay? Here, it's going to shift to the right, okay? Let me walk through this with the balance analogy too. I've not been doing that, but that's what I used on the video and in the lab a little bit. So here it'll shift left towards the reactants. So balance analogy. Let's think about the one we just did, ozone. If we're increasing the concentration of ozone, it's like we're adding weight to this side of the balance, okay? So this side of the balance would tip down. Now, when I drew the upward arrow a minute ago, I just meant that we're increasing the concentration, okay? But that doesn't mean we're tipping the balance up on this side. Okay, that's just a different notation. Whoops. Let me just erase that upward arrow. So it's like we're adding weight to this side of the balance. So the balance would tip down on this side. When I say this side, I mean the right side. The balance would tip down on the product side. So to get them even again, we would want to take some ozone and run this reverse reaction to make more oxygen. If we make more oxygen, we're going to add weight now to the left side, okay? And that would help restore the balance to even, okay? So that's why we say it will shift left, if you like that balance analogy. Okay, adding a catalyst. What is that going to do to equilibrium? Nothing. It will make the reaction reach equilibrium faster, but it will actually not shift equilibrium at all. So if you want to think that's a trick question, but catalysts aren't involved in the reaction. They're not either a reactant or a product, so they're not going to shift equilibrium either way. And then increasing the temperature, okay, increasing the temperature. So let me erase what I wrote up here. Increasing the temperature. So we need to consider what our delta H is again. I'm gonna highlight that. Our delta H here is positive. And because it's positive, we can think of heat as a reactant. Heat plus oxygen, 3 moles of oxygen will give us 2 moles of ozone gas. So if we're increasing the temperature, if we're increasing the concentration of heat, we could think of it like that. Then we're tipping the balance down on the reactant side, okay? So because we're adding heat, LeChatelier's principle says we want to use up some of the excess heat. The only way this reaction can use up some of the excess heat we added is by reacting it with oxygen and making ozone, okay? When you run the forward reaction, it uses up heat. It absorbs heat because we said this is an endothermic reaction, okay? And then that would kind of bring the level of heat back down to normal. We added heat. We have an excess of heat. We want to use some of it up. The only way we can do it is by running the forward reaction, which uses heat plus oxygen to make ozone. So here, equilibrium will shift to the right. And then I'm going to add a 6th scenario because I think this will be helpful to y'all. What if we decrease pressure? And I'm going to do this. What if we decrease temperature? So these will be the last two that I go over. Decreasing pressure. Well, if we decrease pressure, we said this side has more moles of gas because we got 3, and this side has fewer moles of gas because it only has 2. So if we decrease pressure, LeChatelier's principle says we're going to shift to the side of the equation with more moles of gas. So that means we're going to shift to the left, okay? So if we decrease pressure here in this equation, equilibrium will shift left, okay? Now again, don't think that a decrease in pressure always means a shift left. For this equation it does because this is the side with more moles of gas. But you could have a different equation where there are more moles of gas on the product side, okay? So think of a decrease in pressure is always going to shift to the side with more moles of gas. An increase in pressure will always shift to the side with fewer moles of gas, okay? Here, those directions happen to be right for an increase in pressure, left for a decrease in pressure. Okay, lastly, decrease in temperature, and then we'll shut this down. Okay, remember that heat is on the reactant side. So if we decrease temperature, it's like we're reducing the amount of heat on this side. We're taking some away. Okay, we took some weight off of this side of the balance, the reactant side of the balance, and that side of the balance tipped up. So to produce heat again, to make more heat, the only way the reaction can make more heat is if it takes ozone and converts it into oxygen plus heat. That's if you think of taking this and running it to this side, we're producing heat that way. Okay, if you're thinking of it in the reverse reaction. Overall, we read the reaction normally from left to right, where heat is a reactant plus oxygen makes ozone. But if you're looking at the reverse reaction, then you have ozone is going to make oxygen and heat. Okay, so if we took some heat away, because we decreased the temperature, we want to generate more heat. The only way the reaction can do that is by running the reverse reaction here. So equilibrium will shift to the left. Okay, I hope this was helpful. There are many other practice problems right around this one, 7.6, 7.62, that you can check in the back of the textbook because they're even. But I hope this was helpful, and we'll do more practice next.